This video is a summary of the magnetism topic for AQA GCSE Physics, and it is for both GCSE Physics and Combined Science. So this content appears on paper 2, and this video is going to focus exclusively on just a summary of the topic. So it's not going to go into the most maximum detail that you could in every area, but it is going to give you a really strong overview of everything you need for the exam, and should enable you to revise really effectively, especially the night before. So let's get into it. So magnetism, the first thing you need to make sure that you are clear about is how to draw basic magnetic field diagrams. It's really common that you're asked to distinguish these. So you have to know how to do it for a bar magnet first of all. And so the key features that you're looking for here is that the shape of a magnetic field around a bar magnet, I always kind of describe it as a little bit like a butterfly, in the sense that you've got the wings, kind of the loop and circle from one end to the other, and you've sort of got like the antennae and the tail that kind of poke out of the poles. But more important than that, what you have to recognise is the fact that the magnetic field is based on loops. It's based upon the idea that there are field lines which go out of the north end of the magnet and go around into the south end of the magnet, and the direction is always north to south. So that's the first and probably the most sort of overarching diagram that you need to know for the shape of basic magnetic fields. That same shape is going to recur in other aspects. So the second sort of follow-on to that is then, what does it look like if you have attraction between two bar magnets? So you should know that opposites attract, so a north pole and a south pole will attract each other, and so the field lines from the north pole will extend directly into the south, and the direction is always north to south. That never changes. You should also be able to demonstrate what it looks like for a magnetic field of repulsion between two bar magnets. And so in that case, in this diagram you can see a north and a north shown. All of the field lines must kind of veer away from each other. So they kind of come towards each other but never meet, they never touch. So they kind of come in and then veer outwards. And obviously we would loop all the way back round into the south at the other end, just like the top diagram. And obviously because this diagram is north against north, all of the arrows point out of the end of the magnet. If this diagram was changed to a south and a south, again that would be repulsion, but the arrows would be pointing inwards. So that diagram would effectively be the same, but the arrows would be pointing in rather than out. You need to understand that there are two types of magnets, okay? So the types of magnets that we talk about are permanent and temporary or induced magnets. You should be comfortable using both terms, temporary or induced magnets. So a permanent magnet is anything that produces its own magnetic field. Examples of this are like steel. So steel is an alloy of iron and carbon. The iron is magnetic, but the impurities from the carbon mean that the iron, once it has been magnetised, retains that magnetism. We'll talk about how it gets that in a second. Now, temporary magnets, you need to know examples of these, and there are three that you should know. You should need to recognise iron, nickel and cobalt as the three magnetic metals, magnetic materials that are all form temporary or induced magnets. They all have the ability to be magnetised. Now, temporary magnets are defined as that they become magnetic when they're placed inside a magnetic field, and they can kind of hold on to that magnetism and kind of retain that for a while at least, but eventually it could be lost once they're kind of removed from the field, etc. Now, there's one really important thing here. We've already talked about the idea that if you have opposites, they attract. North and south will attract, and like poles, so north and north or south and south will repel. But there is a fourth option, and the fourth option is the one most people miss. It's also something that's highly common to come up on the exam because everybody forgets the fourth option, and that is what happens if, instead of bringing a north and a north or a north and a south together, what happens if I bring a magnetic pole on, like say a north, near to a temporary magnet. So a temporary magnet isn't magnetic until it's placed inside the magnetic field. So if you were to imagine that diagram over here on the left hand side, instead of having the like where it says attraction, you've got north and south. If the other bar pole here didn't have any poles on it, but it was just a temporary magnet, it's not magnetic yet, and this bar magnet approached it, the outcome is always attraction. So if one question that's really common is you've got three unknown materials, one is a permanent magnet, one is a temporary magnet, one is unmagnetised. How can you tell them apart? So unmagnetised materials will obviously just not respond to the presence of a magnetic field. A permanent magnet can both attract and repel, and it's the repulsion that's important there, depending upon its alignment of its poles to another secondary permanent magnet brought towards it. A temporary magnet will always be attracted to a permanent magnet. think of like your magnet on your fridge. If you've got fridge magnets, you can't make those repel. They stick to the fridge or they don't, but there's no repulsion side to them. It's the same kind of thing. Why are things magnetic? So if we're explaining this concept, we have to understand the idea of magnetic domains. So if you were to zoom in into the surface of the bar magnet, what you would see is what almost looks like fields, like as in field, like patchwork feels like farmers' fields, but made of the metallic substance, because they kind of literally form this kind of pattern where groups of atoms will align with each other, almost just like mini magnets inside a magnet. We call these magnetic domains. So the really important language for you to use here is, in an unmagnetized material, magnetic domains are randomly arranged, like this diagram here. You see they're all pointing in all different directions. Like, imagine this is lots of mini magnets and they all cancel each other out. In a material that's magnetized, I'm just going to move me for a second, the magnetic domains are all aligned to be in the same direction. So that creates they align with the direction of the local magnetic field, and that therefore increases the strength of the magnet overall. So that is pretty much it when we're talking about magnetism. Now the rest of the module focuses on electromagnetism, so everything shifts attention now. So the big idea of this is, anytime you have a moving charge or a moving current passing through a wire, or in any other context, it produces a magnetic field. In other words, electricity produces magnetism, and magnetism generates electricity. When you have one, you have the other. So any moving current or moving charge produces a magnetic field. So this is advantageous because you can turn current off and on, and so you can turn the magnetic field off and on, and that's why electromagnets are very, very useful. We can also increase the strength of the magnet by increasing the current and things like that. So one diagram you need to know first with electromagnetism is, what does the magnetic field look like around a single wire? So if I've got a single wire and a current passing through it, and for this we use what is known as the hitchhiker rule, or the right hand rule. And so what you do is you hold your thumb up and you have your fingers around, and you imagine you're grabbing hold of the wire. Your thumb points in the direction of the current and your fingers will show the direction of the magnetic field. Now when you're trying to do this, it's really important you can, from the diagram, work out which way current is going. So you can see this view here, like the isometric view that's shown first, where you can see just the wire going up through like the plane, and you can see that the current is just indicated with an upward arrow. That's nice and easy. But one thing that often happens in your exam is the direction of the magnetic field will literally be coming out of the paper towards you, or into the paper away from you. So it's easy if it's up, down, left or right, but how do we show and explain stuff coming out towards us or away from us? So the language we use for that is into the plane of the paper or out of the plane of the paper. And the way we show that is we use dots and crosses. So a dot indicates the tip of the arrow. So if you see a dot, that means that it's coming towards you out of the plane of the paper. Think of like your finger pointing at you, that's like the tip of the arrow. The cross indicates like the back of the arrow. So think of it like, if you think of like an old-fashioned like Robin Hood type arrow, you have the feathers at the back of the arrow, the fletching. That basically forms like a crisscross pattern if you kind of look at it. So think of that as the back of the arrow. So a cross indicates the back of the arrow. So how is that shown in diagrams? So here is one diagram where you can see there's a dot in the centre. That dot isn't a random dot. That dot is telling us that the current is coming out of the paper. If you're looking at the screen now, that means that the dot is coming out of the screen. So when you use Fleming's right, not Fleming's right hand rule, when you use the hitchhiker rule, which is with your right hand, where you've got your fingers wrapped around your thumb should be pointing towards you, okay? And there your fingers are going to be in a clockwise direction, which is why the arrows are indicated on that diagram. So you can see that the diagram of the magnetic field around a single wire is actually very easy. It's just concentric circles, and they get slightly further apart the further away you go to show that the field gets weaker. The hard bit is knowing which direction is the field, so for that you have to use your right hand, so it's the right hand hitchhiker rule. This would be the diagram if the current was going away from us. So now you can see the X in the middle, that's the back of the arrow, so that means it's going into the plane of the paper or into the plane of the screen. So in summary of that point, the right hand hitchhiker rule, which we use for a single wire, the thumb indicates the direction of the current and your fingers indicate the direction of the magnetic field. So the next thing we have to then explain is motors. And so we can take that single wire and we can wrap it round to form a solenoid, which is a coil of wire. And the solenoid has a magnetic field just like a bar magnet, but the magnetic field passes all the way through the centre of the coil and it's constant inside that coil. We can then use that coil and place it inside between two of the bar magnets. So this is our motor. So in our motor we have two magnets, like two permanent magnets, and they have their own magnetic field. We have placed a coil of wire in between them, which has the ability to rotate, and we put a current through that from a power supply, so like a cell, and that current obviously generates a magnetic field. That magnetic field repels the magnetic field of the permanent magnets, and so causes this to rotate. Now, one feature that's important here is the end, which is called the split ring commutator. So at the end of it, we have this ring at the end, which has got this gap in the middle. That's the split element of it, the split ring, and it's connected to these brushes. And so the role of the split ring commutator is it means that the coil of wire can keep spinning in the same direction. A bit like if you turn your hand over, you can only go so far, because your hand doesn't have a split ring commutator. Like, it turns so far because it basically your bones in your arm, your radius and your ulnar, cross over each other and it can't continue to turn. But we want a motor to be able to continue to spin. So what the commutator does is allows that rotation in one direction to keep happening because the ring breaks every half turn. So we have to be able to explain this confidently, and there's 5 key points you must be able to articulate to describe how a motor works, which we'll go through in a minute. We also need to be able to describe, like, in terms of how the forces are being applied on this motor, and for that we use Fleming's left-hand rule. So Fleming's left-hand rule, first of all, it has to be your left hand, okay? So it has 3 elements: your thumb, your first finger, and your second finger, and they all have to be pointing 90 degrees to each other, so that's really important. There's no crooked hands in this, you have to point them all straight. And my advice is, if you use Fleming's left-hand rule on your exam, you must follow the order. So do first finger, second finger, thumb. First finger, second finger, thumb. So your first finger, all the F's, is the field. It's the direction of the field, which is always north to south. So if you're using Fleming's left-hand rule, the first thing you're going to do is you're going to point from north to south, whichever direction that happens to be. So on the motor that you can see here, we could point from left to right, because that's the direction of north to south. Then we stick out our second finger at 90 degrees. That is the direction of the current. So on the motor diagram you can see at the bottom, you can see that the arrow for the current is pointing towards us on the left hand side and away from us on the right. So if I do the left hand side first, we've already established that the current, the magnetic field is north to south. We point the current back towards us, so when I stick my thumb up, that indicates the direction of the motion. So that means on the left hand side here there's going to be an upward force on the motor. And if you do the same on the other side, the magnetic field is the same, but the current has now changed direction. So we turn our hand over, and so you can see when I stick my thumb out, the motion is downwards. So this coil is going to rotate clockwise. So the left side is going to go up, the right side is going to go down, and it's going to spin. So second finger is the current. Think of second, the K for current. And your thumb, the M in thumb, is for motion, or the direction of the force, if you find that easier to think about. So that's Fleming's left-hand rule. So remember, those 3 things you need to be able to state: what is the first finger, second finger, and thumb, but also the idea that they all have to be 90 degrees to each other. This is the 5 points you then need to be able to explain in terms of a motor. So the detailed explanation is that a flow of current creates a magnetic field around the coil. That's this point here that we talked about. Any moving charge or current creates a magnetic field, so you articulate that first. The magnetic fields of the coil and of the magnets interact. So make sure that you're clear there about the fact there's 2 magnetic fields, one from the coil, that's the electromagnet part, one from the permanent magnets, and they interact. The opposite sides of the coil experience force in opposite directions, and we've just talked about in this example, the left side would be upwards and the right side would be downwards. That's what we're using Fleming's left-hand rule. And then the final 2 points are you should be able to explain how the split ring commutator works. So it ensures that current continuously flows in only one direction, and the way that it does that is that it does it by reversing the direction of the current every half turn, because every half turn, that gap creates a momentary break in the circuit, but because it's spinning with momentum, it continues to spin. It kind of almost like catches itself on the same side, which means that the polarity seems the same on each side of the ring at any one moment, so it's constantly turning in the same direction. We can use and one equation to describe this. This is only going to be on the higher paper if you are doing it, so it's not on the foundation paper. The equation to describe this is F equals Bill, so that the force on any current carrying conductor inside a magnetic field is the magnetic flux density or magnetic field strength multiplied by the current times the length of the wire inside the field. And that has to be in meters. So very commonly that is given in centimeters, so watch out for that conversion. And sometimes they try to put the current in milliamps, just to be a little bit tricky. The magnetic field strength is typically quite a small number, because 1 Tesla, which is the unit of magnetic field strength, is actually quite a large unit. So very often, like the Earth's magnetic field, for example, is 50 microtesla. So that is 5 times 10 to the minus 5. So it's quite a small number. So often magnetic flux density or magnetic field strength is again quite small. So just be aware of that. So that gives you a detailed summary of the magnetism topic in terms of like all the key things that you need to know for combined science. And so this gives a pretty good overview of all the main things you need to make sure you revise. If you know everything that is covered on this summary, you should be in a pretty secure place when you go into the exam. I will just say that there is a few extra topics here that are covered in the triple topic, so you do need to be conscious of those. So if you do triple science, you also need to look at generators, which are like the opposite of motors, transformers and the national grid. A little bit more detail on those, but that's not covered in this video. All the best in your exam and happy revising.